Hello and good evening in our study of linear algebra. In this lesson, we'll talk about symmetric matrices. So let's look at a definition. The matrix B is said to be similar to matrix A if there is a non-singular matrix P such that B is given by P transpose AP, where P is the columns of P are the eigenvectors of matrix A. Okay, so for example, let's consider our matrix A. Okay, then in order to obtain matrix B, we find the eigenvalues of matrix A, then we find the corresponding eigenvectors of matrix A. Okay, so we determine the determinant of the matrix A, that's given by we find the eigenvalues of it, that's A minus lambda I equals to 0. Then we find that we'll get two different eigenvalues. Okay, so after obtaining the eigenvalues, you'll find the corresponding eigenvectors using this relation A minus lambda I V equals to 0. Okay, so after obtaining eigenvalues, you get two eigenvectors, and here are the eigenvectors. One of the eigenvectors will be 1 1 and the other eigenvector will be 1 2. Okay, so from this we find the inverse of matrix P. That's 1 over the determinant of matrix P times the adjoint of P. So the determinant is 1. Okay, that's 1 times 2 minus 1 times 1, so that will be 1 over 1. Then the adjoint, we swap you consider the leading diagonal, you swap the element in the leading diagonal, then you negate the element in the other diagonals, right? So you swap 1 and 2, then you negate the other end, that's 1 and 1. So that will be 1 negative 1 negative 1 1. Okay, so we find our similar matrix B given by this, that's P transpose AP. Okay, so this is P inverse, this is matrix A and this is matrix P, and we get towards 2003, where 2 and 3 are the eigenvalues. Okay, so let's consider the following elementary properties, okay, of similar matrices. Okay, so first one, A is similar to B, and if A is similar to B, then A is what? Similar to A. Or in other words, if B is similar to A, then A is similar to B. Okay, also if A is similar to B and B is similar to C, then A is similar to C. Okay, that's the transitivity property. Okay, that's the transitivity property. Then we see that the matrix A is diagonalizable if it is similar to a diagonal matrix. In this case, we also see that A can be what? Diagonalized. Okay, A can be diagonalized. Then we also we see a theorem that similar matrices have the same eigenvalues. We're not going to pay much attention to the proof. Okay, now let's consider another theorem. So an n by n matrix A, okay, is diagonalizable if and only if it has n linearly independent eigenvectors. Okay, so when you have any matrix, okay, such that the eigenvectors of that matrix are linearly independent, then we say that that matrix is diagonalizable. In simple words, you see, we know that matrix P, the columns of matrix P are the eigenvectors of matrix A. Okay, so if the eigenvectors of matrix A are linearly independent, it means that when you construct them in a matrix P, when you use the eigenvectors to form your matrix P, I earlier said that columns of matrix P are the eigenvectors of matrix A. Okay, so if after constructing matrix P such that the columns are the eigenvectors and these eigenvectors are linearly independent, it means that the determinant of the newly generated matrix P is non-zero. And if the determinant is non-zero, it means that that matrix P is invertible, or in other ways, matrix P is non-singular. Okay, that's why that makes what matrix A diagonalizable. But if the eigenvectors are linearly dependent, it means that the matrix P, whereby the columns of P are the eigenvectors, the determinant of matrix P will be 0. And therefore, we see that matrix P is singular. And singular matrices are the same as non-invertible matrices. It means that the inverse does not exist. Okay, and therefore matrix A is not diagonalizable. Okay, I hope this is clear. Okay. All right. Then another theorem says that if the roots of the characteristic polynomial of an n by n matrix A are all distinct, then A is diagonalizable. So the roots of the characteristic polynomial is the same as eigenvalues. Okay, after you have used the relation, the determinant of A minus lambda I equals to 0, your value, the values of lambda, that's eigenvalues. Okay, is the same as the root of the characteristic polynomial. So if the eigenvalues of an n by n matrix are all distinct, then A is what? Diagonalizable. Okay. All right. Now let's move on to so you can try your hands on this question. Yeah, you can try your hand on this. Okay. So with this, we form your matrix B, such that before then you find A, such that the columns of matrix P are the eigenvectors of matrix A. Then you solve for matrix B. But the elements from the leading diagonals in matrix B are the eigenvalues of matrix A. Okay. So let's move on to diagonalization of quadratic symmetric matrix. Okay, so when you have a quadratic form, then you can rewrite quadratic form Q of x y z as x transpose ax, where x is given by x y z. Okay, so when you have your quadratic form and you want to diagonalize it, you have, let's see, when you have a symmetric matrix A is symmetric. Okay, when you have a symmetric matrix A, then the similar matrix B is given by P transpose AP. Okay, P transpose AP. This time around, it's not the inverse, it's actually the transpose. That's when you have any symmetric matrix. Okay, and the columns of P are the normalized eigenvectors of matrix E. Okay, in other words, matrix P is what? Our modal matrix. Our matrix P is a modal matrix. Okay, so for this particular matrix, first of all, we find the eigenvalues of this matrix. Okay, so when you do that, you get 3 different eigenvalues. And you see all the eigenvalues, 2 of them are positive and 1 of them is 0. Okay, and therefore the nature of this quadratic form is what? Positive semi-definite matrix. Okay, that's matrix symmetric matrix A, that's positive semi-definite. Okay, so here are the corresponding eigenvectors of matrix A. Okay, and they are orthogonal. Therefore, we can generate our modal matrix P from using the eigenvectors of matrix A. Okay, using the eigenvectors of matrix A. So here is our modal matrix P. Okay, and now when you solve this, that's P transpose AP. So if we have this as P, then P transpose is given by 1 over root of 10, 3 over root of 35, minus 3 over root of 14, 0, 5 over root 35, then minus 1 over root 35, minus 3 over root 14, 2 over root 14, then 1 over root 14. Okay, that's transpose of what? Matrix P. Okay, and you can use it to generate your diagonalized matrix B. Okay, using this relation, P transpose AP, this P transpose, this matrix A, and this is matrix P. When you do that, you get this matrix, a diagonalized matrix, and the columns, the elements on the leading diagonals of matrix B are the eigenvectors of are the eigenvalues of matrix A. Eigenvalues of matrix A. So you have another question. Okay, so we have quadratic form. So this is what we have. So we split the cross product terms into 2. So we split 8xy into 2. That's 4xy, 4yx. Can also split 4xz into 2xz, 2zx. Then 4yz into 2x, 2yz, 2zy. Then you generate your matrix A. Okay, and here is A, x, the coefficient of x squared, that's what? Element on the first row, first column, that's 5. First row, second column, x for this, from this quadratic form, or x is for row number and y column number. Okay, row column. So actually x is for 1, y for 2, and z for 3. Okay, so for xy, that's element in the row 1 column 2, that's 4. Row 2 column 1, also 4. Row 2 column 2, that's 5. Row 1 column 3, that is 2. Row 3 column 1, also 2. Then row 2 column 3, 2. Then row 3 column 2, also 2. Then row 3 column 3, 2. So this is our symmetric matrix A. So from here we can find our eigenvalues of matrix A. Okay, and this is how we find eigenvalues of matrix A. That's minus lambda cube plus the trace of A lambda squared minus the principal minor of matrix A lambda plus the determinant of matrix A equal to 0. Okay, and the trace of matrix A is the sum of the diagonal elements of A. The principal minor is the sum of the minor of the diagonal element. Then the determinant, it's clear. Okay, so you can use that to generate the eigenvalues of symmetric matrix A. Generate eigenvalues of symmetric matrix A. And you use eigenvalues to generate the corresponding eigenvectors of matrix A. So here are the so we have 3 eigenvalues. We are getting distinct roots. That's 1, 1. We are getting repeated roots rather. Okay, 1, 1 is the repeated root. Then also have the distinct root. So here are the corresponding eigenvalues of matrix A, eigenvectors of matrix A. Okay, and they are to go now. So you can now diagonalize the matrix. So you find B such that B is equal to P transpose AP. Okay, and when you're done, you should get 1 0 0 0 1 0 and 0 0 10. Okay, based on how you arrange your matrix P. 1 0 0 0 1 0 then 0 0 10. Okay, so let's look at another example. We have this, that's f of uv. You have to prove let Q be a quadratic form associated with a symmetric bilinear form F. Show that the polar form is given by this. There should be a minus sign here. Okay, so first of all, let's consider the right hand side of the equal sign. So we have this. Okay, so we can rewrite each term. As what? Symmetric bilinear form. So Q of u plus v is given by f of u plus v, u plus v. Then Q of u, that's f u u. Then Q of v, that's f v v. Okay, so we can also split the first term into f u u. So pick this u, then we match it with this u. You pick the first u, you match it with the second, that's the v. So we have f v u, and also have f v v minus the other terms. Okay, but f u v is the same as f v u, so they are like terms, and therefore we can combine them. So when we do that, we get 2 f u v, and we have f u u minus f u u, so it cancels out. Then we also have f v v, then minus f v v, it also cancels out. So we are left with this, and from here we can just divide 2 by 2. When we do that, we get this, and that is the proof. I hope it's clear. Okay, so there are more examples. Okay, on diagonalization of matrices. So here matrix A. Here are the eigenvectors of A. Okay, so use eigenvector to generate matrix X. But remember, A is not symmetric. So generating similar matrix B, we use this relation X inverse AX or P inverse AP, such that X or P, the columns of X or P, are the eigenvectors of matrix A. So when you do that, this is the inverse of matrix A. Okay, matrix X. Then this A, then this also X. Okay, so when you simplify, you get a diagonalized matrix, and 6 and 1 are also the eigenvalues of matrix A. This means that similar matrices also have the same eigenvalues. Similar matrices have the same eigenvalues. And this is another example. So we have our matrix here. This matrix 2 is not symmetric, right? So you find your eigenvalues from this matrix A, and you continue to find the corresponding eigenvectors of matrix A. Then you formulate your new matrix X such that the columns of X are the eigenvectors of matrix A. So we have eigenvalues, then here are the corresponding eigenvectors. So you generate your matrix X, and the columns are the eigenvectors of matrix X. So, but since A is not symmetric, we find the inverse of matrix X, and this is the inverse of matrix X. Therefore, our D is given by X inverse AX, and when you simplify, you get this matrix. Okay, thank you for watching.